Uh, Professor Sridhar, sir. Sir, please switch off your video, sir.
Thank you, sir. Thank you, sir. Thank you.
Sir, good afternoon, sir.
Good afternoon. Thank you. Thank you so much. Sorry, there was a small this thing. I was not able to enter inside. Thank you. So, should I start? So,
1 minute,
sir. Sir, 1 minute, sir. We will start, sir. Sir, Professor, sir, shall we start, sir? HOD,
yes,
sir?
yes. Go ahead, sir. Go
Yes.
ahead.
Oh, okay, sir.
Sir, so let me go to my screen also. Okay, okay. Please finish. Please finish.
Yes, sir. Yes, sir. Please, sir. Good afternoon to one and all present here. I welcome all the participants to this fourth phase 6-day short-term training program on nanotechnology and functional materials. Now we are going to start this first day, second session. Once again, we thank all the participants for joining with us. Now let me introduce our resource person, Dr. J. Ramkumar, professor from Indian Institute of Technology, Kanpur. He has completed doctoral degree from IIT Madras in 2003. His fields of interest are microelectric discharge milling, microelectrochemical milling, excimer laser micromachining, etc. He has published more than 480 research articles in international and national journals and conferences. His citations are 2347, H index is 25, and I-10 index is 56. He was honored with many awards and fellowships, and here are the few glimpses. He was a gold medalist in MTech IIT Madras 2000, Innovation Potential of Student Project Awards, Indian National Academy Engineering in 2004. He has received Young Scientist Award from Engineering Science Division, Indian Science Congress Association in 2007. In 2007, he has received Young Scientist Award from Department of Atomic Energy, India. In 2010, he has received Rajkumar Varshini Awards from System Society of India. In 2010, he has received IEI Young Engineers Award. He has received Class of 1984 Fellowship Award from 2012 to 2015. We are honored with your presence, sir. The topic of this session is two-photon lithography for nanotech structures. Now, I request our resource person to proceed with the session, sir. Requesting, sir.
Yeah. Thank you so much for a wonderful introduction. So I don't know whether I deserve it, but thank you very much. You have presented it nicely. So I would like to share my screen. So your window, I just wanted to, yes, window
Yes,
share. Okay. So are you able to see my window?
Yes, sir. Coming, sir. Yes.
Two-photon polymerization.
Yes, sir. Now it's perfect, sir.
Okay, okay. So thank you very much for to the organizers for giving me an opportunity. So really, they are taking a lot of efforts in connecting experts with the people who are interested to learn. And this online is really helping us because traveling to Tirupati and giving a talk and all will be really cumbersome. I'm able to connect with you people and I'm able to talk. And thank you very much to all the vibrant minds who are present and who have shown a lot of interest in attending my talk. So thank you very much to you all. So the first thing what we will discuss is we will try to see this two-photon polymerization, where is it used? So we will see it first. We will see different types of machining. Okay. So first way is called as subtractive. Manufacturing can be divided into two parts. One is called as subtractive process, and the other one is called as additive process. Or if you want to talk in terms of top-down approach, bottom-up approach. So when we start talking about subtracting process, it is called as top-down approach. In top-down approach, we start with a huge chunk of material and slowly start removing this material, and finally we try to get an output. In many of the aeroplane parts today, they try to start with a chunk of material and they slowly start milling, removing it and make it lightweight and complex structure. They try to use it. So even now, exhaustively subtractive machining is used. Okay, subtractive machining, as I told, is not a sustainable machining process. Here, you start with a huge chunk and then finally you try to get whatever output you want. Okay, so almost all the conventional machining process and non-conventional machining process which are available today follows this route. What is the advantage? Majority of the processes, what we are trying to do in the subtractive process, you can increase the speed. So material removal rate is very high. You can do multitasking at one point, and you can try to produce huge strength of material. And the last one is going to be, to a large extent, you will try to have homogeneous property across. Okay, suppose let us assume you wanted to make nano features, which is 10 to the power minus 9 nano features. Okay, if you want to make that, and if you start with 1 millimeter substrate and going to the level of making a 10 to the power minus 9 meter feature, it is next to impossible. Next to impossible. It is very difficult. If you use any of the heat assisted process, it is going to melt. If you use a etching process, it is very difficult for you to control. Okay, if you use ion beam, electron beam, again, it has its own limitations. Laser also has its limitations. So now, subtractive process, which is though very efficient, we have been using it for long, but now there is a big need for developing this additive process or bottom-up approach process. In bottom-up approach process, what we do is we try to make small building blocks and try to carve out whatever we want in that building block and start assembling those building blocks such that we can make the required output whatever we want. Okay, so those things are called as additive manufacturing processes. To a large extent, the starting material can be a powder, can be a wire, can be a liquid. Okay, you cannot have a gas, but you can also, apart from gas, because we are trying to build a three-dimensional object, you can always argue that PVD process, CVD process, they are all 2.5D processes. That means to say along the Z direction, they have a standard height, but in XY plane, they can go to any extent, whatever they want. Okay, so gas cannot be thought of. So it can be either a liquid or a solid. So when you talk about solid, it can be either in the form of a powder, it can be in the form of a wire, or it can be form of a sheet. Solid, when I say. Okay, when you go to sheet, what happens? There is always a limitation that you will not be able to produce exactly the feature size whatever you want. So sheet is out. So now what is left with you is either you start with a liquid material, or you start with a powder material, or you start with a wire material to develop the object whatever you want right from the beginning. So here you can see the material, whatever is available, is all in loose form, powder form. And now this powder is getting assembled. And they try to join and they try to develop a 3D object. So if you look at it, there is a huge energy saving which happens by using this additive process. Earlier, this additive process was only thought of for prototyping. Now what is happening is we have started moving into the era called as rapid manufacturing. In rapid manufacturing, what happens? Whatever output we get from this additive manufactured process, we are directly putting it into good use. So now additive process is coming up in a very, very big way. And now the next question comes. In additive process, can I make nano features or can I make nano parts? Next to impossible, sir. If you have a starting material, see, if you have a starting material, I told you it can be in the form of a powder or it can be in the form of a wire. Moment you have a nano powder, once you start putting this powder, it will start having a phenomena called as agglomeration. What is agglomeration? Agglomeration is nothing but when particle to particle, they get stuck onto each other. When they get stuck onto each other, single powder you cannot generate. You will have a cluster of powders. And when you start working with nano materials, you will try to have this problem of clustering, or they try to form agglomeration. So you cannot have nano size. So you will always be happy by using a micro size or by using a wire form. You will be start using these two. But moment you see a powder which does not stick, then the powder size becomes large. Moment the powder size become large, now can I use it for nano features? No, it is not possible for you to use for nano features. So wire is gone, now powder is also gone. So what is left with us is liquid. So if you have starting material as a liquid, and by some hook or crook technique, if you are able to convert this liquid into a solid, then you try to join the solid. You can try dot, you try to have a liquid, you do something and then it converts into a dot. Several of these dots stuck together forms a line. Several of these lines stuck together forms a plane. Several of these planes stuck together forms an object. So now what is happening is, with liquid as a starting material, by using some jugaad technique or by using some repeatable, reliable, scalable technique, I try to convert the liquid into a solid. Now, can I make nano features or micro features? Is it possible? Yes, it is possible. Now, what brings that change? From micro to nano, it is nothing but the source, what you apply for polymerization is important. Moment you apply a source for polymerization, so then you convert a liquid into a solid. Now, what dictates? The spot diameter dictates. If I can focus it to a very small diameter of 10 to the power minus 9 or 10 to the power minus 6 meters, then I am able to do polymerization of a single spot. Moment I do for a single spot, now what I will do is I will try to join these spots and try to form a line. Moment I try to form a line, I try to form a line, then what we will do is we will try to change it. We will try to give a solid object to it. Okay, so that is what is happening in this additive process. Starting material, liquid. So naturally, you cannot have a liquid solid material, liquid material like ceramic. You cannot have. You cannot have metal. So what is left with you is polymer. So if I can do polymerization by using a source, right? By using a source, if I can do that, then that is used for making this additive manufacturing. So my building blocks are nothing but the single spot. Several spots are nothing but several small building blocks joined together to form a line. Okay, so here the biggest advantage is going to be, since I am constructing it from my from the building block, I dictate the process. Okay, I dictate also the shape and size I want. Now the polymer material today has grown up like anything. You can have a conducting polymer. So once you have a conducting polymer, you can apply field from outside. It can start moving left and right. It can start running. It can start jumping. It can start expanding. It can start contracting. So all these things you can do. So in that way, you will see that additive is going to be the future as far as nano is concerned. So here are some of the comparisons between additive manufacturing and subtractive manufacturing. So additive manufacturing, we always use this, we always try to develop it layer by layer by layer. We use a 3D printer to make the product. 3D printer means we are trying to use a machine where XYZ is there. Using that machine, you are trying to assemble and join. So the end result will always have some surface roughness that needs to be finished. So that is the problem with the additive manufacturing. Because when I was talking about a building block like a spot, so when several spots overlap, you will try to have a small roughness on the surface. And since it is doing layer by layer, you will always try to have an object which is anisotropic in nature. It is ideal for small parts. The process is slow. So rapid prototyping does not happen within 3 minutes or 5 minutes. It takes time. Then you can make very complex parts very easily. For example, if you want to do this, a cube, if you want to drill a hole, so here is a cube where all the sides of the cube, you have drilled a hole of uniform diameter. So if you want to do it by conventional machining process, you will have to do multiple settings. You will have to do minimum 3 settings, right? But whereas in additive manufacturing, the entire object will be formed in one setting. So that's what very complex parts can be made. It is economical. And the 3D printing, rapid prototyping, and additive fabrication are also part of it. When we talk about subtracting, it is very well known, so I will not go into it. So these are some of the additive manufacturing processes which are available today. To start, let me start with LOM process. In LOM process, we are using a layer material. So here it is like a laminate. So it is used for making micro parts. Then comes lens process or directed energy deposition process. It can be lens. Lens is laser engineered net shaping. They also can use electron beam additive manufacturing, EBMA. So here the beam, laser and electron beam are changed. When you talk about electron beam, the resolution size can go smaller. But with the electron beam also, going to nanometer is a big challenge. And second thing is, when you start working with electron beam, it demands a vacuum chamber, and it is not so easy to handle such things and develop a part. So today you have electron beam additive manufacturing machine available for 3 crores onwards. Whereas lens, laser engineered net shaping, here they don't demand any chamber or vacuum or whatever it is. You can directly use the laser and try to hit on the object and start doing it. But both puts again a limitation on the powder size. Next, you can also use binder jet process. It is just like your inkjet printing. So then material jet, it is like your color printer. So these jetting processes are all very same. So you can use a ceramic and then you can jet adhesive there, or you can try to heat it and then throw the jet there. So that is material jetting. It is possible. Then the other way around is you can extrude and then start developing it. But finally, when you have all these things, you will see that there is one process which comes up in a big way is VAT-assisted photopolymerization processes. VAT-assisted photopolymerization process. So in VAT-assisted photopolymerization process, we use a laser. We use a laser, and this laser writes on polymer. So now here what do? I try to control the diameter, and I also try to control the polymerization which happens in the VAT. So now by using the laser, and interestingly, laser are always selective in nature. For example, a laser which is used for polymer, if I start using metal as a polymer as a workpiece, now I change the polymer workpiece with metal, can I do it? Very difficult. Maybe it will do, but it will not give the expected output what you want. Okay, it might not give that. So in that case, what happens is you should understand this. For laser gives you a freedom of selectively doing polymerization. When we talk about laser, there are only 2 types of mechanisms with laser. One is called as pyrolytic action. The other one is called as photolytic action. Pyrolytic action means the laser hits the surface and you try to induce a lot of heat there. So the heat converts the solid into a liquid to vapor. And when we use this pyrolytic laser, you will always see there is a moving melt front which keeps moving, and when you start writing it. The other way around is photolytic action. Photolytic action means here you try to use the laser and convert the liquid into a solid. That is called as photolytic laser. Excimer laser, UV laser, majority of the time used for this application. So now it is very clear, when somebody has to do a nano texturing, it is, and if you want to do additive manufacturing process, the first thing what you should come is you should think of using laser. You should think of using a polymer. And the mechanism behind the polymerization is photopolymerization. Light is used to do polymerization. So now these three processes, what is given here? SLA, cured with laser, cured with LED and oxygen, cured with projection. So all these things are used. What is cured with projection? It is very simple. You think of a mask which you keep in front of a light. For example, you put a torchlight, keep your hand in front of it, you see the shadow. Now what happens? The shadow is nothing but a projection. What happens? And every time you keep replacing the hand with another hand. So then what happens? Every time a layer of information is exposed, and once the layer of information is exposed, the photopolymerization happens. One full layer of polymerization happens in one shot. Okay, so when you go to this SLA process, what happens? It is just like writing a paper, paper with a pen. So you write the pen on a piece of paper, and it does writing. So it is by using laser writing, the object, whatever you want to do polymerization, that will be exposed, and a laser will go make the spots and dots around it and try to develop one single layer of information. The other way around is you don't want laser, you want to economically do it. People have also started using LED. So this process, wherein which you start using polymers, liquid polymers, and exposing it with LED or with laser. When you expose it with LED also, it depends upon the wavelength. It will be a UV wavelength, it will be a blue, or it will be deep blue, or it will be ultraviolet. Okay, that is used, and then we make that information. When we talk about this additive manufacturing, it has been slowly started growing. So you see here this stereolithography. Stereolithography means you are trying to build a 3D object by using lithography techniques, which is nothing but projection techniques. And what you do is you do develop layer by layer by layer by layer information, and you stack it, and then you try to make a 3D object. If you see that the business for stereolithography has been growing exponentially from 2015 to 2026. The laser sintering is the other process, but you cannot think of making nanotextures here. So this stereolithography, you play with the liquid, you play with the laser, and then you start making textures. So these are some of the 3D printed micro nano textures which are exhaustively used today. Lot of electronics and communication devices are 3D printed on polymer substrate, so it is made flexible. Moment it is made flexible, the activating, deactivating becomes very easy. And printing on top of a polymer is always a challenge. So what people do is they try to develop 3D micro and nano textures using polymer. There are a lot of micro optics which are getting printed today. Micro optics which are printed today, the shape, size, and the material. All these things, they do a lot of simulation. They make a combination, and after getting that combination, they try to print. They try to print the optics. The optics again are also polymer optics. Okay. Then in biomedical field, there is a lot of application which they use this nano texturing and micro texturing using polymer substrate. Then for MEMS, where they talk about exhaustively lab on chip culture, so they talk about MEMS, and then they talk about metamaterials. They talk about metamaterials, which is again exhaustively used. So metamaterials are those materials where where the electromagnetic radiations or waves are absorbed by the structure and they don't emit. So this is exhaustively used for stealth applications. So here also they try to make this micro nano features. Okay, so look at the dimension, 20 microns. This is 20 micron scale. So now this will be around about 40 microns you can have. And on that you can have some small textures which is made. Okay, this is again microfluidics lab on chip which we talk about. So here one droplet of blood or fluid is used and they try to analyze what is it. So in the area of doing all this nano texturing, and then following the route of polymerization, there is a concept which is called as two-photon polymerization technique, which is used exhaustively for building micro and nano textures on top of surfaces. So what is this two-photon polymerization? Normally, what happens when you try to expose one packet of H nu of your preferred wavelength, right? And when you try to expose it on top of a polymer, so then what happens is the polymerization process happens, and you will try to see a small dot there. Okay, you will see a small dot there. Now what is happening? You will try to see the small dot. So that is called a single photon polymerization. When we talk about two photon polymerization, when the light is exposed on top of a polymer, the electron moves from the ground state, it moves to a virtual state and it stays there, and it will not stay there for infinite time, and this parking time also will be in nanoseconds. So now what, it will get parked there. Now you apply one more photon, it goes to the excited state. So this is why it is called as two photon. In two photon, they are basically used to polymerize a place by using two photons of H nu. Two photon polymerization is another additive technique. In this process, instead of single two photon are simultaneously absorbed by the substrate to undergo the polymerization. That means to say, when two photon hits at a surface, it has to be the same, like one after the other or whatever you say. So it has to be in that way. And then it will try to polymerize and it will try to move to the excited state. So when we try to see the second figure, you can see that these are the H nu atoms passing through the lens, and these are the photons. You keep the object on the focal plane, or the liquid is adjusted such that it is a plane inside the vat. So what you do is that is now exposed with photons, and you try to develop a single layer of information. So you can either use a continuous laser or you can use a nanosecond laser. Since this is two photon, so we always try to use a pulsed 600 pulsed laser, UV laser, where in which you can see the temporal confinement happening. And once the temporal confinement happening, you will try to have polymerization of a small dot. So what I'm trying to impress you is, impress you saying that additive manufacturing is used for making nanotexturing by using the concept of two-photon polymerization. Okay, so a little bit more about two-photon polymerization. Single-photon polymerization directly proportional to the intensity. More the intensity, more will be the polymerization. So here the process is said to be linear. Single-photon polymerization. When you talk about two-photon polymerization, the relationship is not linear. You will have a quadratic dependency of the intensity. That means to say, first four shots or 3 shots, nothing will happen. When the 5th shot comes, you will see a big polymerization happening. So a single photon absorption, and I have put a 2-photon absorption. Note, excited energy levels S1 and S2, shown below are not exactly the same, since the selection rule of a single photon and a 2-photon absorption are different. The main advantage of multi-photon photon microscope are high spatial resolution and the ability to selectively excite specific molecules you can do. See, when you use a UV laser, you can try to do selectively in the sense, selectively some molecules alone you will cure, or you can say selectively in terms of a plane where you want to do polymerization. Okay, so both things are possible. The main advantage of multiphoton microscope are high spatial resolution and the ability to selectively excite specific molecule. Okay, so we will try to see some of the basics of two photon basics. So when you try to use a photopolymer, and initiation is nothing but when you start giving the intensity, two photons, H nu and H nu, two photons are hitting. So it tries to have I star. I star means there is polymerization started, and R, that leads to R. So now R is nothing but front. So there is a propagation. So now this propagation happens for R plus M giving you Rm. So now what is happening is there is a lot of polymerization happening. So M square bracket R MM, that leads to R into Mn. So that is nothing but lot of mers joined together to form a polymer. So then once by this time what is happening? The growing is happening. Polymerization is happening. Now the next, how will you stop it? So that stopping happens through a termination. So termination happens through the free radical R and Mn plus R plus Mn. So now what happens is R plus N plus M, when these two fellows join together, they will try to stop the process. Okay. Now the next question comes is, what is the rate with which it can absorb? The rate with which it can absorb is, it directly depends on d omega by dt, which is given by 8 pi r squared omega. So if you see very closely, where have you seen this formula? It comes almost close to that spot diameter, this diameter in laser, EDM, EBM, all these things you get. 8 pi square omega divided by n square c square. I is the intensity, I into m, which is psi to the power 3. So that means to say it is a quadratic relationship. And here we try to talk about the wax width. Generally in a computer, what we talk about pixel. But when you talk about 3D objects, we talk about a term called as voxel. That is nothing but minimum volume pixel. So now when you talk about a volume means there will has to be a length component and there will has to be a width component, and then you will have a z component. So that is nothing but the width, volume width. So that is found out by this formula, and the length is found out by this formula. Whereas C is nothing but a natural logarithm of rho, which is the power intensity with which you try to hit, and PTT rho TH is the threshold value after which the polymerization can happen. So if you look at this figure very closely, you can see that the spot diameter happens. So this is 2 photon region. You can see a spot hitting there, and moment there is a spot hitting there, there will be polymerization happening in the x direction and z direction, and this is called as the voxel. So you can see a spot. Now what happens? This diameter, the dimensions of the spot, it can be in nanometer. It all depends on the focusing lens, right? Focusing lens, and it can start the volume. That is the Z you have, and width and length can be adjusted to the space, whatever you want. So here, the focused laser beam, when you try to hit at a polymer, this thing, but you can see here, it not only cures on the surface, it can also cure below the surface. So these are some of the textures, structures, which has been developed by using this 2-photon polymerization. You can see here how complex is this animal. You can see here a windmill. The scale, you please watch the scale, 14 microns. If this is 14 microns, what is this feature size? You can see tree-like structures which are made. Now these tree-like structures are used for enhancing the surface area. So in a battery, now people are talking about why don't we have carbon tree-like structure? So where in which the surface area is enhanced. So from a small area, you see there is a large area enhancement. And again, all these things will be in microns or it will be in nanometers. Okay, you can see here the spider has been made. The entire thing is 15 micron. When you look at it, this will be 1 micron. And when you look at the legs, it will all be in nanometers. Okay, so additive manufacturing is used. Additive manufacturing, when we use 2-photon lithography, you are able to develop 3D objects. When I say lithography, lithography means you are exposing light on top of a mask, and when that light hits at the workpiece, then it starts doing polymerization, or that starts forming a layer. So Nanoscribe is a company which makes such nanostructures on polymer surfaces, which are used for various applications. And Nanoscribe machine is pretty expensive. These machines are costing around about 3 crores or 4 crores, depending upon the specification. So by using it, you can start making, and inside this machine, the 2-photon polymerization is the process which happens, and this is a liquid with which all these things can happen. So the cost of it is 1.4 crores, depending upon your requirement. You can also get a 7 crore machine. So if your feature size is small and if you want to add color to it. So they have been regularly improvising the machines. So what we developed in our lab was we started developing an indigenous the 2-photon setup. And what we did was we effectively used a microscope. And why did we use a microscope? Because if we put a mask and then if we try to allow laser to pass through the mask, and then if we could have a magnification or a demagnification, so then it will try to focus or defocus on a spot. Now, if we just played with the excess 10x, 100x, whatever is given to the optical microscope to the objective field, and then we could develop a small setup. Our setup is not working for nano texturing, but we could do a lot of micro texturing, through which we published a lot of papers. So here what we do, we developed it indigenously. It is developed by my student Gagan, along with the collaboration of Professor Anant Ramakrishnan and Raghavendra. A lot of students were involved. See, anything which gets published from IIT Kanpur or from a good institute, you will always see a big team behind it. It's not me, it's my team did it. Okay, so here what we did was we used a diode pump solid state laser, laser keyhole. The maximum of the laser is allowed to pass through the keyhole. Okay, you have used a diode pump solid state laser. So the output of the laser comes out and it passes through a keyhole. The maxima of the laser is allowed to pass through. We have several dichromatic lenses which are in between. These dichromatic lenses, the laser produces 2 wavelengths. Our laser, whatever we had, produced 532 and 1064. We allowed only 532 nanometer, and we jammed or we damped 1064 nanometer. That is doing your dichrome mirror. So then we had an acoustic modulator. The acoustic modulator, it gives the feedback in the form of voltage on which to switch on-off the laser has to happen. So acoustic modulator, it gives the feedback in the form of a voltage on which the switch on-off can happen. So this is an acoustic modulator, and then we started developing it. So if you see there from a diode pump laser, you have a keyhole, and then the keyhole, both you will have 1064 and this and that. So 1064 is damped, and 532 is further passed into a mirror. From that mirror, it passes through a keyhole, then it passes through an acoustic attenuator. From the acoustic attenuator, it passes through a keyhole, then mirror, then we used an inverted microscope. From the microscope, it started projecting it on the XY stage, and we could develop a single layer of information. But the Z height was constant. So several of these layers, when you start building one above each other, it is going to form a 3-dimensional object. So we developed this 2-photon polymerization process in our lab, and the liquid, whatever we used, was commercially available in the market. We did not develop anything new for the liquid part of it. We used what is available off the shelf, and then we started developing it. So there are 2 types of autofocusing. See, when we start talking about all these things, the next important thing which comes into our mind is how do we focus? Because we are trying to talk about nanometers. So then how do we focus? So how do we focus? So the focus is we have two types of focus. One is we will try to have optical based focus. The other one we will try to have image based focus. So optical based focus is you try to use a lens. Okay, so this is how it is. You use a CCD camera, then you use a connected optical system, then we connect it to the mirror, and then we try to see a sample. So all these things are there. So this is optical based. But what we did in our machine, because we were trying to develop a low cost machine, we were trying to take a look at the image based hardware. So image based hardware is after every polymerization or after a certain level of polymerization, we will always try to take a snapshot. And with that snapshot, we will try to see how much is the deviation which has made. If the deviation is not much, then we will continue. If the deviation are much, then what we will do is we will reiterate, change it, and then we will start moving it. So we have this image-based hardware. We have optical-based hardware. The Nanoscribe had a optical-based hardware. Nanoscribe. And the image-based hardware is what we were trying to develop. So in image-based software, what we did was we had a acoustic modulator. We have an AF acoustic actuator. Then we had a lens. So we had a drive circuit made. Then image sensor. Then image processing. AF algorithm we used, and then we started looking into how do I make sure the autofocusing happens. So the effective of laser spot you see there. The focused, you can see here there are three in one plane. We have taken three lines. The focused position represents the LFS. Okay, LFS, laser focal spot. So the focused position represents LFS, laser focused spot, with zero deviation in the EA1. B1, what happens? The width of the fabrication increases with indicates variation in LFSC. Then the third one you see no fabrication at all indicates LFS is not is out of range. Now what happens is by taking the image, if you have a blurred image, then we can quickly try to find out the formula theta. And from theta, what we can do is we can start correcting the image. And then based upon the correction, we will try to do in the next step of exposure, we will try to have along a straight line and we get the best out of it. So effect of laser spot, focal spot in experiment, you see that LFS is the place where polymerization takes place with perfectly focused laser beam. So the other methods of focusing are we use an image technique which is cheap, which is economical, time consuming is very which we have now iterated it and made it in very short time. Then we used optical sensor based techniques which are very precise, but it is expensive. We did not use it. So we went around developing image based techniques for finding out what is the deviation from the spot what we gave and what got developed. So now we take an image, and that image we try to do several correlation techniques to make the required output. The first one what we developed was novel focus technique, image correlation algorithm. Those of who are working in image, for you it is very, very trivial. You can easily understand. Those of who are working in mechanical engineering, it might be slightly tough. And I will not have so much of time to cover cross correlation method in a deeper sense. Okay, so I would request you all to read it, and if you have queries at the end, we will discuss. The cross correlation is a computer based on the size of the picture, frequency, and spatial domain. Okay, is computed based on the size of the picture, frequency, and spatial domain. To process the calculation of local sums by pre-processing runs, which we do. So first itself, we try to run pre-process, we understand the system, we calibrate the system, and then we do. The process of cross-correlation uses local sum to normalize the cross correlation to get the cross correlation relationship. So what we do is you have a set of data. This set of data is very erratic. Now what I do, I normalize the set of data. Moment I normalize the set of data, I try to get a pattern. And that pattern, what do? I try to cross correlate with my original data and then see what is the deviation, do the correction in focusing of the laser such that I get the best out of it. That is what I do. Here F represents the image and T average represents the mean of the template, and FU comma V average represents the mean of F of X comma Y in the region under the template. The equation of MATLAB is given, and you can use this. It is directly available in MATLAB. It is directly available in MATLAB, so you don't have to worry much, but you have to know what to plug in and how. So in that way, we have to be a little more careful. So that is where we have to use this formula, U, V, everything I have given. So the other thing what we developed is we have developed something called as Structural Similarity Index, SSIM method. So here what we did was we developed one another technique. So this is used for better iteration. Okay, in Structural Similarity Index method, the procedure to calculate the similarity index in the SSIM code, again this is available in MATLAB, which is the measured between the two images as shown in mu x, mu y is the average value of x and y respectively. Sigma square and sigma square x and sigma square y are the variance. Sigma xy is the covariance. C1, C2 are the variables to stabilize the division with weak denominator. So by using this SSIM x comma y, I am trying to able to get better correlation of the output whatever I want. So both of these methods use one focal image. So you take an image and then look at the image, process, and another image is unfocused to evaluate the correlation. So first you take a spot, then you take an image without a spot, then find out whether it is an image without a spot, then you will try to open the camera, allow it to expose, and then try to get another spot, check with the correlation, and if there is a mismatch, you will try to say, okay, there is a mismatch. So such beautiful algorithms are developed today. So if you try to take a full image correlation with selecting RIO, okay, you will try to get this. When the image is converted into binary, so first of all, what you do is you try to take an image, and then you try to convert the image into. You try to take an image, and then you try to convert the image in a binary form, and then binary form, whatever it is, you try to convert this into edges, and then you try to take the edges, and then you try to connect these edges to get the full image of it, right? That's how you do it in image processing. Here it is in nanometer. I use an optical microscope image, so that tries to do a zooming, and with that zooming I try to do all these X deduction. When the image is converted into binary image, more than 70% of its area is not differentiable. So you have to also set a threshold value. So if you set a threshold value more than 70, so there is going to be reflection and you are not trying to get the data. So I am trying to find the threshold value. So and the correlation index with cross correlation method, then there will be a non-variation and you try to get it. So if you try to plot it with correlation index with respect to depth of focus is your Z. You can see here exactly at 0 what is the correlation index you get is more, and when you defocus it, depth of focus in microns, when you are 40 microns away, you see how the correlation index is. So if the correlation index is poor, so then you are not trying to get the good output. So then what we did was we did the optimization on the region of interest. The ROI, whatever I've said here, is region of interest. Okay, so those region of interest is selected, which can then give us a proper insight about the changes in the image due to laser focal spot variation. Okay, so totally 9 regions of interest we took. So along a straight line, and then from 50 pixel in the length to 450 pixel, we got it, and then we did a cross correlation method, and then we applied that cross correlation method, and then we started getting what is the image. So look at the image, whatever we did. So A shows the maximum region of interest to 450 pixel in the X direction. Then the region of interest in the previous study, whatever we did by other techniques, was studied up to 50 pixel. So now you see here, we could get a better correlation, we could get better accuracy, and the laser will, now this input will be given to laser, and all these things will happen in situ. The first time what we do is we understand all these things, put all these correlations inside the laser, and then try to work on the auto-focusing and try to get the output, whatever is the output we try to get, and that output we try to use it for regular this thing. So now we did some error analysis to find out the data. Error analysis in every region of interest has been performed. So along a straight line, I took at several pixels I took. So pix 50 figure shows the maximum variation and the minimum variation in pix 150 and pix 200. So we try to get this variation, pix 50 and then maximum variation of pix 150 we got, and then we did this cross correlation. We were trying to do the error analysis. So from these three things, what we can conclude is the average, the range of error with pixel 50 is the largest, and the range of 150 is the smallest. So more the number of pixels, you get more the number of data. The drop in the error of 10x can be seen when there is a pixel of 50 to 200 you take, there is a variation you can see here. So here I am talking about pixel 50, 100, 100 correlation. You can see the error. So the error goes down when you take 300. And when you go more than 300, what happens? The dissolution of the pixel happens. So you will try to get a blurred image. Moment you try to get a blurred image, the error goes on. So you can see, therefore, we have selected 200 as our optimum range. And this led to faster processing, and the accuracy, whatever we got, was very high. So hence, both the methods, cross correlation and SSIM, have been used to evaluate the image, and this evaluated image will be given back to the system. So you look at it, if I convert this 200 pixels into microns, it is 78 microns. Our focus was to develop more on microns. We did not try to focus on nanometers because we had a limitation of the wavelength of laser. We had a limitation, so we did it with microns. So when we tried to do SSIM index and we did a cross correlation index, you could see that very good cross correlation index was got from SSIM, and depending upon the depth of focus. So comparing these two, so we could get SSIM method shows a linearity than the cross correlation method, which helps in differentiating between the focused and the non-focused image, determining each threshold value of Rayleigh numbers, which will control the laser focal spot variation. So it is there. So SSIM takes less time, and 25% of the time is reduced. So you can see there. Now I do polymerization, I take an image, I try to find out what is the deviation, accordingly go back and try to control my autofocus. Why? Because in my machine, whatever I have developed here, I don't have the facility of autofocusing. And autofocusing, what do I do is I attach it with a nanometer stage, and that nanometer stage is attached to piezo crystal, and it tries to contract very fast to produce the good output. So these are some of the large area polymerization which we have created. You can see here we have created these textures, and these textures were developed on top of this polymer. This is the IIT Kanpur logo. This is 20 microns. So you look at the features, whatever it is there. And why are these features little blurred here and there? They are blurred here and there because of the spot size. We were trying to focus only on micron because our application what we wanted was micron. So that is where is the small deviation. If I use a nanosecond laser, a femtosecond laser, if I use, then I will be able to get a very clear features. But I am developing a low-cost machine using a nanosecond laser, and I am trying to use pulse, follow the attenuator concept, damp 1064, and get the output for polymerization. So if you look at this figure, we have created smoothering of the surface of the dimples, whatever we have made. So this is going to, this will be used as a dye, and this dye will be used for, making, this is like a stamp. So now what we do is we used to have this as a stamp, and we used to pour polymer, try to replicate the image on a polymer, and then what we do is we do annealing or something. So there is a uniform shrinkage happening. We will try to get nano textures or nano features. Okay, so these are the things which we develop through our machine. So these are the spots which we have developed on top of a polymer sheet for various applications. So now to conclude, I first discuss about the additive manufacturing is a need of the hour. 2-photon polymerization can be worth hair of additive manufacturing. Economical 2-photon polymerization setup was developed in the lab. So yeah, MATLAB code has been developed to generate XY coordinates of the image. See, whatever image, you should understand, if you wanted this image, I have to give this image as a JPG, convert that JPG into some form, such that the laser can pick up those data, and then you can start making the textures whatever you want. So that's what we are talking about. The MATLAB code has been developed to generate the XY coordinates of the image, which can be used in LabVIEW program for polymerization. Canny edge defect filters, deduction filters. These are all edge deduction, because when you try to draw a straight line, there is a place where there is a demarcation of the pixel level, the grayscale level. So then when we try to join all those pixel levels together, what we get is an edge. So canny edge deduction filter was found to be the best method for edge detection of many given images. In the autofocusing of TPP, using the image correlation code, the error analysis has been done, and an optimized region of the interest for the image of microscope movement was developed at 200 pixels. SSIM method is efficient compared to that of a cross correlation. See, when you look at this setup looks as though it is a lab setup. Now we have developed it into a machine. We are trying to convert this into a machine, and we are trying to sell this 2-photon machine which we have indigenously developed. The big difference between NanoScribe and our machine is NanoScribe is able to make nanometer feature, but many a times you don't need nanometer features. We are happy with microns, and we are happy with 5 microns and 10 microns. Then this is a machine which can be used for making very large area texturing of polymer surfaces. With that, I would like to complete my talk. So if there are questions, I would like to take those questions.
And thank you, sir. Now I request participants, please, if you are having any question, you can ask directly to our resource person, or you can type your question in the chat box. I request once again the participants, if you need any clarification, please ask question directly to our resource person. He is ready to answer your question, or you can type your question in the chat box. Sir, one question, sir. Actually,
image processing technique is employed for
that question is from Madam, sir, in YouTube. That is posted our faculty only, sir. The question is, what kind of image processing technique is employed? That time you are explaining that image processing technique, sir. That time that question is asked, sir. What kind of image processing?
Can Madam be more clear in her question, please?
Sir, actually, she is in YouTube live. She is viewing this seminar, sir.
Okay.
So that's why
there are several image processing techniques. I don't know what is your application. We have used these 2 correlation techniques. We take an image, then we try to calibrate it. We try to find out the number of pixels and which one gives the more calibration we see, and then we identify that spot. Then what we do is we do offline calibration first, and that information is fed to the lens there. So the lens, whatever you see here, now, okay. Am I able to share my slides or?
Sir, if possible, you can share, sir. 1 minute, sir. I will ask our.
Right.
Yes, sir. Yes, sir. You can share, sir. Yes, sir.
Okay.
Yes, sir.
Uh, is it visible now? I don't know.
1 minute, sir.
Share.
Yes, sir. It is coming, sir.
Okay, but it should show me that two photon. No? Okay.
Yes.
Are you able to see now? Yeah, just 1 minute.
Sir, yes, sir.
So when we look at this machine, what we developed in our lab.
Sir, sorry, sir. It is not shared, I think, sir. It is not visible.
Just 1 minute, please.
Yes, sir.
Where is it show all? Where is the sharing option itself is not there, sir.
Sir, you can give present now, sir.
Sorry. Yeah, correct.
Yes.
Okay.
Yes,
So in this, if you very closely see, so this is the complete setup we developed. So if you look at this, we have put an inverted microscope. This microscope, either you attach this microscope with a piezo crystal so that you get a quick response, or you attach the stage with the piezo crystal. So here this auto correlation, whatever we are doing is, we are trying to do the image, whatever we get here, with the image what we want.
Sir, voice is not audible, sir. Sorry to disturb you, sir. Sir, we are not hearing your voice, sir. Dear participants, please wait. As due to some technical problem, resource person has left. He will join immediately. Please wait.
So, sorry for inconvenience. Sir has got some technical problem. So please post your questions in chat box. So he's going to join within 2 to 3 minutes. Okay. So he's going to answer the questions. Please type your questions in the chat box.
Thank you, sir. So I request all the participants, please type your questions and do you need any clarification? Please type it in a chat box. Resource person will join within 2-3 minutes. He will answer your questions.
Please type your questions in the chat box, or you can directly ask our resource person.
Sir, once the resource person arrived, I will ask this question, sir. Professor Pravat Kumar Swain, sir. We have seen your question and we will ask, sir, once a resource person has arrived.
So now I am back. So Abhi, I am ready to take on. Sorry.
Yes, sir. Yes, sir. One question in chat box, sir. Shall I read it, sir?
Yes, please.
This question is from Professor Pravat Kumar. Is it possible to go beyond two proton lithographic for nanostructures?
No, sir. See, this itself is, if you really want to focus, it goes to picosecond laser, and picosecond laser stability is a problem. The machine is around about 1.5, the nanoscribe is around about 1.5 crore, large area is around about 4 crores. So now you tell me, what is the justification we have, except for making fancy, small textures? See, apart from that, this cannot do much. And when you start working on polymer can only be used as a stamp. Okay, you make a texture that will be made as a stamp. Now, using that stamp, you can either pour some liquid on top of it, you try to get a structure, or you try to use it like a stamp, like a rubber stamp, you try to stamp it on polymer. So by doing so, you can try to get large area. And where did we use it? We designed textures such that it can be used for thermal imaging of metamaterials. So that means to say, we will try to kill the thermal radiation which gets emitted from the body. So for that, what we did was we made these textures. Okay, so it is possible. There is a science limitation is there, but as such, I myself don't find a lot of applications. Apart from publishing, you don't find applications. So it is no point going further down in nanotexturing. Okay, so any other question, please?
Thank you, sir. Now I request all the participants, please, if you need any clarification, please ask question directly to our resource person. It seems, or you can type the question in chat box. We will ask on behalf of you.
But this is going to be the future, sir. This two-proton polymerization in the area of nanotexturing and polymers they do. And you should also understand, after doing this nanotexturing, what will I do? That is the other question you will ask. So now what people are smartly doing is people are smartly polymer. See, they are trying the polymer once it is cured, they are trying to carbonize it. When you try to carbonize it, it becomes a completely black object. Now with the black object, this becomes an electrode. Now with this electrode with a larger surface area, they are able to make high efficient batteries. So that is where people are now working.
Thank you, sir.
So there is a lot of applications. So am I able to share my screen?
Yes, sir. 1 minute, sir. Sir, Rajesh, sir, kindly, yes, sir. Now you can share your screen, sir, please.
It is not allowing me to share, sir.
Present now and Windows, sir.
It is not allowing, sir.
1 minute, sir.
Present now, Windows. Okay, now it is allowed. Okay,
yes.
so the image what I have put here. Where is that? Okay, the image what I have placed here. Now what people are doing with that A image. See if you can see the pointer here I'm sharing. So this tree image, you see that what is the image what you wanted, and this is what got developed from the machine. And this, what they do is they try to grow like this, several of these trees on top of a surface. Now what they do is they have optimized the process parameters. Now they try to do carburizing cycle. In carburizing cycle, they make sure that the X, Y, Z axis, all the shrinkage happens uniform. They tailor make the polymer in such a way, when you do that carburizing, all these polymers get converted into carbon, and this carbon is used for various applications. So this people are now exhaustively trying. Where large area enhancement of carbon textures. Carbon is used for storing lot of charge. So you can do it. Okay. So any other questions, sir?
Yes, sir. Sir, one more question in the chat box, sir. I will continue, sir, now. This question is from Professor Pravat Kumar. Is there any particular number which can be deviated during error analysis?
Sir, is there any number? So what, okay, you mean to say the error percentage? So error percentage, sir, suppose you want to make a 100 micron feature, you try to take a tolerance of 1/10 of it. So you are allowing it 100 microns means 10 microns. If you are talking about 10 micron feature, 1 micron. So if you go into nano, we try to maintain less than 10 micron, 10%. See, 10% of the feature size, whatever you make. That is a thumb rule. But this thumb rule is not valid in nano, but however, in nascent states now, they are allowing it. See, here, you are only particular about this thing. Now look at the dimension, what is here. Okay, it is very less. Look at the geometry, which is less. And now if you want to take some reference and measure, now you tell me which will be your reference. So there are a lot of challenges still in nanotexturing. Micro nanotexturing, there's a lot of challenges.
Yes, sir. Sir, Professor Pravat Kumar, sir, do you want, you can elaborate your question, sir. You can unmute and you can speak, sir. Okay. Sir, he is satisfied, it seems, sir. Okay. Thank you so much, sir. I request once again, participants, please unmute yourself and you can ask questions or you can type in chat box. Sir, shall I go to vote of thanks, sir?
Yeah. So if there are no questions, I would
yes,
like to just give 1 more minute. If there are no more questions, I'll be happy.
Yes, sir. Yes, sir. Yes, sir. Please, sir.
Very good lecture, actually. One thing is, sir, that 2-photon polymerization means how it is going actually. Polymerization, is it an ordinary polymerization or something?
Sir, ordinary polymerization will happen in 1 photon, sir. In 2 photon, what happens is there will be 2 photons which simultaneously hit. First fellow will initiate the process. Next fellow will freeze the process.
Okay, okay. Thank you very much.
See, two photons simultaneously. That is what in the. Let me share my slide. This thing. Stop sharing. No, I am still presenting. No. So let
Yes,
me
sir.
go to the definition I have put here. See, you see here, two photon polymerization. Are you able to see my screen? Two
Yes, sir. We are
photon
seeing.
polymerization is another additive technique. In this process, instead of single two photons are simultaneously absorbed by the substrate to undergo problem. Instead of a single photon, two photons are simultaneously absorbed. So it goes from the ground state to virtual state to the excited state. So polymerization happens. And I told beginning itself, laser gives me a freedom of selectively doing polymerization. So that is why I stopped 1064 nanometer and I allowed 532 alone.
Okay, okay. Thank you, sir.
Right, sir?
Thank you, sir. I request the participants. Sir, one more question from Professor Sudhakar, sir. The question is, can multiple photon complex polymerization also possible?
Sir, two photon, which when you fastly move two photon itself, you will have something like multiple photon only. You will have almost the same effect. But now the question comes is nano, how fast can you move? You also have a limitation in the hardware and the image also. So a combination puts a limitation.
Okay.
And all these machines will not grow further, sir. These machines are all lab scale they use, and people use it for few applications in selective applications only. So there will be not lot of research going on in this development of these machines further. So say for example in car, there will be already every time there will be 100 people competing with each other to deliver a customer because there are more number of customers. Here, since the domain is very specific, you always will have a limitation. Science will put a limitation. Okay, sir. I will take
Yes.
one more last question and I'll wind up.
Yes, sir. Yes, sir. I request dear participants. I request dear participants, if at all any question, you can ask
Okay.
your.
So, sir, let us go, sir. I think we should not also pressurize them.
Okay, sir. Okay, sir.
Okay.
So, thank you very much, sir. Your presentation added more value for this phase 4 STTP program. The takeaway from your presentations are very high. You have started with the types of machining, additive manufacturing, and the subtractive manufacturing method, agglomeration, and the starting material as a liquid converts into dot, line, plane, and solid. And conductive polymer additive manufacturing is the future for as 3D printer, and VAT assisted photopolymerization and SLA process, then indigenous developed two photon polymerization setup, and the types of focusing techniques are image based and optical based, and novel focusing techniques and image correlation algorithm. And finally, we expand with the pixel 200 is optimization region of interest and large area polymerization. And SSIM method is efficient compared to cross polymer method. Like that, I explained very detailed, sir. Thank you very much, sir. Your presentation is very excellent, and we have gained more knowledge about nanostructures from your presentation, sir.
So, thank you
Yes, sir.
very much. I would like to thank the organizer, the head of the department, the organizing entire team for so nicely you in particular, Madhivanan. So you have consolidated what I presented in 1.5 hours. You consolidated in 2 minutes so nicely. So thank you very much. So I would also request all the audience, you be more vibrant. And I am sure certain things, whatever we talk will be abstract, but you make a note of it. These are all knowledge. These are all developments which are going around. Tomorrow when you see, it will be, oh, I know this process, you will say. So that is what is expected from all these courses. We don't want you to memorize dot to dot. So please enjoy. And the organizing team has put lot of efforts. You have wonderful speakers. All the speakers who are there are all either across the globe top outstanding or across country top outstanding. Ravi Shankar is there, Ajay is there. So many people are there. So and Sudarshan Ghosh, who comes from Delhi, he is a good friend of mine. He is also an outstanding professor. So I would thank the organizer for taking so much of pain in inviting so many people and nicely coordinating with so many vibrant participants. So thank you very much, and I wish everybody good luck and for the workshop best wishes. Thank you.
Thank you, sir. I request our convener, sir, to conclude this session with the thanks to our resource person.
Sir, good afternoon, sir. Sir Ramkumar, sir, good afternoon, sir. Myself,
Yes.
Chandrasekhar Reddy, sir. Sir, on behalf of Management Principal, Department of Mechanical Engineering of SVCE and participants of STTP, thank you very much for accepting our invitation and delivering an informative and a thought-provoking webinar on two-photon lithography for nanostructures in AICTE sponsored STTP on nanotechnology and functional materials, organized by SV College of Engineering, Tirupati, from 2nd to 7th, in spite of your busy schedule, sir. It was splendid presentation which exposed the researchers and facilities to the field practice. Thank you very much, sir. Thank you very much for your presentation. And you told we have gone across all over the globe, sir.
Yes, yes. See, you see, Ajay Sitpara is from IIT Kharagpur. You see,
Okay.
Ghosh is from IIT Delhi. Ravi Shankar from IIT Tirupati. And Som Shekhara, who gave a talk today morning, is also a close friend of mine. He's from IIT Madras. So all of them are, and he talked about this bio cell adhesion. I know him very well. So we were all contemporaries. So he has also given a good talk. So I would really appreciate the organizers to pick so many people. And finally, Pandian, Saundra Pandian was working with us at IIT Kanpur. He's a close friend of mine who was a neighbor. So he is also very good in electronics. So I would really appreciate the organizers for picking the best people. And I wish them all good luck. Thank you.
Thanks for your cooperation, sir. Thanks for your cooperation. You have given phase 3 and phase 4 also, sir. Thank you. Thank you for your cooperation.
Thank you.
Thank you, Ramkumar, sir.
Thank you, sir.
Thank you, sir.
Now I request all the participants, our afternoon session is over. Tomorrow session, sir, Rajesh sir, kindly share tomorrow session, sir. Morning session from Dr. Narendra Pura. Our topic is functional nanomaterials for energy storage application. And afternoon sessions, Professor Dr. Mamila Ravishankar. The topic is nano finishing of biomedical implants using polymer rheological abrasive complex fluids. I request all the participants tomorrow, as usual, please join 9:45. Thank you all.
Madhivanan, sir.
Yes, sir.
Sir, you ask any feedback from the participants so that
sure, sir, sure. So I request the participants, you can discuss any feedback if you want to share with us. Please unmute yourself and please discuss with us, sir. Your feedback will enrich our effort and it will be very useful for us, sir. Please.
So Professor Ram Kumar is great. I have attended many sessions, included in my college.
Thank you, sir. Thank you.